Well, you see, before we wander too far into the deep night, let me ask you something. Something gentle and, a little unsettling in that quiet, cosmic way. What if the simple act of looking at the world actually changes the world you see? It's a strange thought, isn't it? Almost like standing before a mirror and wondering whether the reflection is waiting for you, or, well, whether it has a life of its own. And, that question, tiny, delicate, almost shy, sits right at the heart of modern physics. Quantum experiments, those fragile dances of light and particles, have been whispering to us for decades that reality may not be as solid or as single-threaded, well, as we assume. Perhaps, every moment you and I live is just one version of many, one branch on a vast, shimmering tree of realities. And that's the thing. The deeper we look, the more the universe seems to open, and open, and open again into possibilities. Hugh Everett once suggested that all outcomes, every potential path, might continue to exist. Parallel, silent, touching but never crossing. And, whether that sounds like science or dream, it's carried by the mathematics themselves. So tonight, as you're settling in, maybe tucked under a blanket or lying in the soft glow of a lamp, we're stepping into a story that is not just science, but also something like a lullaby. A story in which the universe isn't a single stage, but, well, a grand theater with countless overlapping sets. Not just one world, many. Not just one thread, threads woven into threads. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, while you're here with me, tell me, where are you listening from tonight? I find it comforting, to imagine this quiet conversation stretching across continents, connecting us in small, gentle ways. It's always fascinating to see who's joining us from all around the world. So let's continue. There is a quiet moment that arrives sometimes, usually when the night settles and the world softens, when a single question drifts into the mind like a small ripple across a still lake. And, it is a question simple enough to whisper, yet vast enough to bend the soul a little. If observing reality changes reality itself, then what exactly are we living inside? Is it a world fixed and certain, or a world that, well, hesitates before it reveals itself, like a shy performer behind a curtain? Hugh Everett, in the late 1950s, stepped into that silence with a thought so strange that even today, it echoes across physics like a gentle but persistent tremor. He asked, what if the world does not collapse into one outcome? What if what if it keeps every possibility alive? Not in metaphor, but in the very mathematics of quantum theory. You see, at the time, the dominant view was that the universe behaved like a kind of cosmic coin toss. We observe, the wave function collapses, and a single result emerges. But Everett, he dared to say that the collapse never happens. Not just never in practice, but never in principle. Every outcome, every shimmering branch suggested by the equations of quantum mechanics continues to exist, each one unfolding in its own version of reality. It's not one world, it's many worlds. And the mathematics doesn't forbid it. In fact, the mathematics seems to prefer it. It is almost poetic, really. The universe, instead of being a simple line stretching from past to future, becomes something else entirely. It becomes a forest of paths, a great and silent branching with each quantum interaction. That, um, that picture unsettled people, and perhaps rightly so. It suggested that reality was not the singular, steady thing we imagine when we wake each morning. It suggested we lived inside a vast structure of possibilities, layered atop one another like morning mist. When Everett first explained this, physicists reacted with something between discomfort and fascination. You see, the idea that all outcomes occur feels extravagant, excessive, almost baroque. And yet, the alternative demanded something equally strange, a collapse of the wave function without any clear physical mechanism. So, it became a choice between two wonders, a universe that splits or a universe that hides part of itself behind mysterious collapses. Neither felt entirely comfortable, but that is the thing about nature. Nature does not seem particularly concerned with our comfort. As I suppose Everett saw it, the equations were quiet, direct, almost stubbornly honest. They described a wave of possibilities evolving smoothly. They didn't describe a collapse. Humans added that part. So, he simply removed the human addition and allowed the mathematics to speak for itself. And the mathematics painted a picture of branching universes. Imagine, for a moment, a simple particle drifting through space. It has a range of possible positions, a spread of possibilities like colors swirling in a pool. When it interacts with something, the universe does not choose one color. Instead, each possibility becomes its own thread. The universe becomes a loom, weaving not just one tapestry, but countless tapestries, each equally real, each equally valid. It's not just poetic metaphor, it's the literal implication of the theory. And, if that sounds difficult to believe, well, consider this. The quantum world is already strange. Particles behave as waves. Waves behave as particles, and certainty appears only when measured. Before that, the world is a haze of maybes. So Everett's bold suggestion was not that the world is stranger than we think, but that it is exactly as strange as the equations say. No more, no less. What moved me, personally, is how this idea shifts our relationship with the universe. It reminds us that what we call reality is not a static photograph. It is a dynamic, unfolding story written in probability. And the page does not tear when one version of events diverges from another. The story simply grows new chapters, quietly, endlessly. Some physicists found the idea unsettling because it redefined what it means to exist. Not just here, but possibly there, and there, and there again across a spectrum of realities. That is a lot to take in. We tend to think of ourselves as singular beings, fixed in one narrative. But Everett's view whispers that we may be more like melodies played across many instruments, each performance slightly different, each one still, in its own way, us. And that leads to another quiet thought. If all outcomes unfold, then what is choice? What is chance? What becomes of the small moments of our lives when we stand at a crossroads? Perhaps the crossroads never truly narrows to a single road. Perhaps every road continues, even the ones we never walk in this branch of the cosmos. It's not just a scientific proposal. It's a philosophical invitation. But even with such beauty, the idea was greeted with skepticism. The physics community of the time found it extravagant because it demanded an infinite proliferation of universes. And, I suppose they wondered, as many still do, if invoking countless realities simply to avoid collapse was worth the cost. Yet Everett insisted that the cost was not his to pay. The equations already suggested it. He merely acknowledged the bill. Quantum mechanics, you see, is not a theory that asks our permission. It simply describes. And if it describes a world that branches, then our task is not to resist, but to listen, to let the universe speak in its own language, however soft and however strange. When I think of Everett's idea, I often imagine standing on a quiet hillside at dusk, the air cooling, the sky deepening, the first stars appearing like tiny questions pricking the fabric of darkness. And, you wait, and you listen to the world around you. In that calm, you may feel that reality is not a single thread. It is a river delta. One river, many channels. One existence, many expressions. Perhaps that is why the many worlds interpretation still fascinates us. It doesn't give easy answers. It gives a wider stage. It invites us to see ourselves not as isolated observers, but as participants woven into a cosmic pattern larger than any individual outcome. It's not that our choices don't matter. It's that they matter differently. They don't collapse the universe. They position us within one of its endlessly branching stories. And the more you look, the more the idea feels less like an extravagant claim and more like a natural extension of quantum theory's quiet logic. Every possibility evolves. Every interaction entangles. Every branch carries forward the full dignity of physical law. There is no magic, only the calm unfolding of mathematics across a vast landscape of realities. So, when we return to that first question, the question whispered in the silence, we find it is not just poetic, but scientifically profound. If observing reality changes reality, perhaps it is because observation is not the act of shaping the world, but of selecting our place within its many branches. And that thought leads us gently, almost inevitably, toward another mystery. Because if reality branches relentlessly at every quantum interaction, then perhaps the structure of the universe itself is shaped by these deep quantum foundations. Perhaps what we call our world is only one ripple in a wider sea. And to understand that sea, we must look deeper into the nature of quantum states, into the strange domain where possibilities hum and interfere before any outcome is ever seen. And that is where our journey must go next, into the trembling heart of quantum theory itself, where reality flickers between what could be and what is, inviting us to listen more closely to the language of the universe. And so, as we step into that trembling heart of quantum theory, we find ourselves standing at the threshold of a world that is not quite solid, not quite definite, not quite willing to tell us what it is until we ask it. And, strangely enough, the moment we ask is precisely the moment it begins to change. Reality, in the quantum sense, is not static. It is not a stone. It is more like a shimmering veil caught in a breeze, moving subtly between what could be and what will be. Superposition is the first whisper of this strange world. It tells us that a particle does not choose a single state. It does not say, I am here or I am there. Instead, it says, I am here and there, and perhaps everywhere in between. It's not a metaphor. It's a literal, mathematical truth. And that is what makes it so unsettling. We expect reality to commit, but quantum physics resists commitment. Imagine a small electron drifting through space. Classically, you would imagine it as a tiny bead, a pinpoint with a precise location. But in quantum mechanics, it behaves like a cloud of possibilities. That cloud is not just ignorance on our part. It is the true description of the electron before we measure it. It is as though the universe hesitates, giving us multiple futures simultaneously, all equally valid until a measurement fixes the outcome. And that idea becomes even more astonishing when we consider the famous double-slit experiment. If you shine particles through two slits, you might expect them to behave like classical marbles, forming two clusters on the screen behind. But no. The particles interfere with themselves, producing a delicate pattern of bright and dark bands, as if each particle has taken both paths at once and created a wave pattern. And, the moment you try to observe which path it took, the pattern disappears. The wave of possibilities collapses into a single storyline. It's not the equipment. It's not human intention. It's simply how nature behaves. Observation is interaction. Interaction is information. And information changes the evolution of the system. It's not magic. It's simply how quantum states evolve. For a moment, try to picture this not as a physics experiment, but as an intimate conversation with the universe. You ask a question. The universe replies. But the reply is shaped by the question itself. It's not that we control reality. It's that we are entangled with it the moment we look. And that leads us to another fundamental idea: entanglement. If superposition is the universe's whisper, then entanglement is its deep and resonant chord. Entanglement says that two particles can become so deeply connected that the state of one cannot be described without the other, even when they are galaxies apart. Not just correlated, but unified. A single system spread across space. Einstein called it spooky action at a distance, partly in frustration, partly in wonder. And, well, for decades, many assumed there must be hidden variables, some secret signals passing between the particles. But experiments in the late 20th century showed, conclusively, that no such classical explanation exists. The universe really does link distant particles in a way that transcends our ordinary sense of space. So, what does that actually mean? It means that the world beneath our everyday experience is not made of isolated objects. It is made of relationships, of connections, of possibilities woven together like threads in an invisible fabric. And those threads stretch, they span, they bind. Not just here, but everywhere. When we entangle two particles, we create a single state that encompasses both. It's not this or that. It's both at once, until measurement disentangles them. And even then, the measurement itself becomes part of the story, part of the universal wave function, part of the branching that Everett described. But I suppose we must be careful. Quantum mechanics is strange, yes, but not mystical. There is no ghostly force reaching across the void. There is no faster-than-light message. There is only the silent logic of the wave function evolving according to its rules. We don't break causality. We don't violate the speed of light. We simply reimagine what reality is made from. Not things, but states. Not properties, but probabilities. Not certainties, but patterns of information waiting to crystallize under measurement. And this brings us back to the double-slit experiment in a more profound way. The pattern on the screen is not the result of particles choosing paths. It is the result of their wave functions interfering. It is a dance of possibilities. When you observe the particle's path, you don't merely watch. You disrupt the dance. You force the universe to tell a simpler story. That is the delicate poetry of quantum mechanics. The universe prefers richness, multiplicity, nuance. We prefer clarity. So measurement is a compromise between the two. It's where our desire to know forces reality to settle into form. And, perhaps this is why the quantum world feels so alien. It is not that the world is chaotic. It's that the world is more generous than we imagined. It allows multiple outcomes. It allows interference. It allows entanglement. It allows the fabric of reality to remain soft until the very moment we press our question upon it. I often think of superposition as a kind of cosmic breath, a long inhale before the exhale of measurement. In that inhale lies everything that might be. In the exhale lies everything that is. We grow older. Clocks tick. But deep beneath it all, the quantum world hums with endless potential, flickering and shifting like candlelight on a wall. And remember this: the strange beauty of quantum mechanics is not tucked away in textbooks or laboratories. It is everywhere. Every atom in your body, every spark of thought in your mind, every photon that reaches your eye participates in this same dance between uncertainty and reality. It is not out there. It is in here, inside the very matter of you. Well, take entanglement again. We often speak of it as though it were an exotic feature of rare particles, but entanglement is the rule, not the exception. It holds molecules together. It governs chemical reactions. It shapes the stability of matter. Even the warmth of your skin, the glow of a candle, the gentle hum of life itself is rooted in quantum mechanical transitions, in probabilities becoming events. So, when we say the universe rests on quantum principles, we mean it literally. Everything you have ever touched, tasted, loved, feared, remembered, is the result of quantum systems interacting. But, and this is important, they only become classical when enough interactions occur to wash away the delicate interference patterns. Reality becomes robust only when the fragile quantum states lose their coherence. Before that, the world is like a symphony with too many notes to count. And, if superposition is the music, entanglement is the harmony. Together, they shape everything from stars to raindrops to the tiny flashes inside neurons that might or might not be part of consciousness. Whether consciousness depends on quantum processes, well, whether it exists at all in that domain remains deeply uncertain. But what is certain is that quantum mechanics forces us to rethink what observation means. We do not stand outside the universe measuring it. We are part of it. Every measurement is an interaction. Every interaction entangles us with what we observe. As one physicist beautifully put it, we do not collapse the wave function. We join it. And, that idea can be unsettling if we cling too tightly to the classical picture, but it can also be liberating. It tells us that we are not separate from the universe. We are expressions of the same underlying quantum fabric. The boundary between observer and observed is thin, permeable, shifting. This is why I think the quantum world feels less like a mechanical system and more like a story. A story written in probability, shaped by interaction, unfolding as we move through it. It's not deterministic in the classical sense, nor random in the chaotic sense. It is something in between, a world guided by amplitude instead of certainty. And as we let our minds settle into that truth, we begin to see how entanglement is not merely a feature of quantum theory, but the bridge to something deeper. It is the glue that holds the branching structure of Everett's many worlds together in the mathematics. And it is the key to understanding how reality divides without breaking, how it multiplies without chaos. So, perhaps it is fitting that our next steps lead us further into that mystery, into the nature of entanglement itself, not just as a mathematical structure, but as a fundamental feature of the universe's architecture. Because if the quantum world hums with possibility, entanglement is the rhythm that connects those possibilities into something larger, something whole, something profoundly shared across space and time. And, well, It is toward that deeper understanding that we now gently turn, letting the quantum haze guide us toward the strange and beautiful bridge between states that Einstein once doubted and modern physics now embraces. And, so we cross that bridge now, stepping gently into one of the most haunting ideas in all of physics: entanglement. That state of being where two particles, once touched by the same moment, become inseparable in their description, no matter how far they drift apart. And, it's strange, isn't it? The way nature sometimes behaves as though distance is optional, as though the separation between things is little more than a polite illusion. Einstein himself found this deeply unsettling. He famously called it spooky action at a distance, a phrase that still echoes across lecture halls even today, in the quiet hours of the night when students try to convince themselves that the equations really are telling the truth. And, well, the truth is that they are. Entanglement is not a trick. It's not a philosophical metaphor. It is something real, solid, measurable, even harnessable in laboratories around the world. But to understand why it's so important, especially for Everett's branching universe, we have to look at what entanglement actually does. When two particles become entangled, they stop being two. They become one system. Not just connected, but unified. Their states interlock like hands woven together, so tightly that describing one without the other becomes impossible. It's not that they exchange messages. It's not that one tells the other what to do. It's that their very identities are shared across the space between them. Well, picture this. Two photons are created in such a way that their polarizations are correlated. You measure one here, and the other instantly reveals a complementary value over there. Not because information travels. It doesn't. But because the measurement simply resolves a property that was never local in the first place. The polarization wasn't hiding inside each photon like a secret. It was spread across both. A single property belonging not to A or B, but to the pair together. That, and that alone, is already astonishing. But what makes it even more profound is that no classical explanation can account for it. For decades, people tried. They invoked hidden variables, little gears or switches inside particles that predetermined outcomes. They imagined subtle mechanisms, collapse fields, whispering signals that darted between particles faster than light. But every experiment, every careful test of Bell's inequality, every increasingly precise study told the same story. No classical picture survives. Nature really is non-local in how it encodes information. And, if that feels unsettling, it's because it challenges something deep in us. We like to believe in separate objects. We like to imagine the universe as a collection of little independent pieces. But entanglement whispers a different truth. It tells us that separateness is an emergent illusion, that beneath the world of solid things is a deeper world of shared existence. So, when Everett proposed his interpretation of quantum mechanics, he saw entanglement not as a quirk, but as the foundation. Every interaction causes entanglement. Every measurement binds observer and system together. And as this entanglement propagates, it creates distinct branches, distinct realities, each carrying a consistent version of events. Not just many possibilities, but many instantiations of those possibilities, woven by entanglement into separate, non-interfering worlds. You can think of entanglement as the stitching that holds each branch of reality together. Without it, the branching universe would be impossible to describe mathematically. With it, the theory becomes elegant, almost inevitable. It's not that the universe splits because we choose. It splits because quantum mechanics demands consistency. Each measurement entangles the state of the observer with the observed system, and in doing so, it partitions reality into correlated outcomes. Consider a simple example. A particle in superposition approaches a measuring device. Before interaction, the particle is one thing and the device is another. After interaction, the particle's state becomes entangled with the device's state. And if an observer looks at the device, the observer becomes entangled too. It continues outward like ripples on a pond, each entangled layer defining a new branch where everything remains perfectly correlated. It's not just the particle that splits. It's the measuring device. It's the room around it. It's the neurons firing in the observer's brain. It's the entire world that carries forward the imprint of that outcome. And, well, this is why entanglement is not just a curiosity. It is the engine of branching reality. That idea bothered Einstein almost as much as it fascinated him. His discomfort, though, was not with entanglement itself, but with what it implied about the nature of reality. If particles could share information non-locally, what did that say about space and time? What did it say about causality? What did it say about the universe's deep architecture? He hoped hidden variables might rescue classical intuition, but the universe, as it turns out, is far more subtle. We grow older, clocks tick, but the quantum world beneath those ticking seconds is constantly weaving threads between particles, constantly creating relationships, constantly redefining what it means for something to exist. Existence, in the quantum sense, is not a solitary affair. It is a shared condition, expanded across multiple entities. And, if you follow that thought far enough, you begin to see why the many worlds interpretation embraces entanglement so fully. In a sense, entanglement provides the boundaries of each world. When two states become entangled, they share a fate in that branch. But when decoherence sets in, that slow spreading of entanglement into the environment, the different branches separate like water dividing around stones. Each becomes inaccessible to the others. Not destroyed, not merged, but simply parted by the expanding web of correlations. It's not out there, it's in here, in the very rules governing how states combine and separate. The universe doesn't branch because we influence it. The universe branches because entanglement accumulates. The world is constantly recording itself, scattering quantum information into the environment. That scattering is what makes the classical world feel stable. We don't see superpositions because the information that would reveal them has leaked into countless degrees of freedom. And, we cannot gather that information back. We cannot unscramble the universe. So, each branch becomes a closed history, an independent storyline. Yet all of them remain part of the same mathematical object, the universal wave function. Entanglement is the architecture that shapes this wave function, defining which states belong together and which no longer interfere. In this light, Everett's picture becomes almost serene. Instead of collapse, we have separation. Instead of randomness, we have unfolding potential. Instead of a single timeline, we have a multi-threaded tapestry of existence, each thread coherent within itself because entanglement preserves its structure. And, perhaps what makes this so beautiful and so difficult is that we ourselves are entangled beings. Every atom in our bodies carries a history of interactions. We are the sum of quantum relationships stretching back to the earliest moments of the cosmos. Our memories, our identities, our choices become part of a branching structure much older and much grander than any individual life. So when we say entanglement is the bridge between states, it's not just a poetic image. It's literal. It is the bridge between what could be and what is in each branch. It is the bridge between the quantum and the classical. It is the bridge between local moments and the universal wave function. Entanglement defines reality by connecting its pieces. And that is why no classical theory, no hidden variable model, no collapsing mechanism has ever been able to match its power. Collapse theories, elegant though they sometimes are, require additional forces or ad hoc rules. Hidden variables require structure nature does not seem to provide. Entanglement, by contrast, flows naturally from the mathematics. It is not forced. It is not added. It is inherent. Imagine for a moment that you follow an entangled system outwards, from 2 particles to 2 molecules to 2 regions of space to 2 macroscopic measuring devices. With each scale, the web of entanglement grows thicker. Soon, the entire experimental setup is unified in a single state. Soon, the observer joins, simply by looking. Soon, the environment participates, recording traces of each outcome in scattered photons, in thermal vibrations, in the soft molecular motions of the air. Decoherence spreads, interference fades, the branches crystallize, and the multiverse grows. And, well, if we pause here, at this edge where mathematics becomes metaphysics, we find something deeply human hidden inside the quantum formalism. A reminder that our experience is only one version of countless versions. A reminder that reality is richer than our senses allow. A reminder that the world is not carved from stone, but drawn from possibility. We walk through our lives believing we inhabit a single thread. But entanglement suggests we are part of a wider pattern, a pattern that continues to expand with every interaction. The universe does not simply exist, it unfolds. And that unfolding is guided by the connections between things. So, perhaps it is not surprising that our next step leads us beyond individual particles, beyond paired photons, and into the sweeping architecture of the universe itself. Because if entanglement binds states together at the smallest scales, then maybe, just maybe, it also shapes the branching of the cosmos. Maybe the universe, in its vastness, is nothing more and nothing less than a grand, entangled system, splitting and recombining, weaving and unweaving, writing countless realities every second. And, it is toward that greater branching, toward the grand structure of diverging timelines, that we now quietly turn, letting entanglement guide us deeper into the unfolding tapestry of the multiverse. And, as we follow those threads of entanglement outward, stretching from particle to particle and world to world, we begin to see something even more astonishing, something almost unsettling in its quiet inevitability. Because if entanglement is the stitching, then the universe itself becomes the quilt, endlessly weaving new patches of possibility with every interaction, every collision, every faint whisper of quantum exchange. And, it is from this ceaseless weaving that the idea of branching truly emerges. So, let us step gently into this landscape now, into the place where the universe divides, not at the scale of planets or stars or even atoms, but at the scale of the tiniest interactions, billions upon billions of them each second. It's not that our choices split the universe, though we like to imagine ourselves at the center of cosmic drama. It's that the universe is already splitting all the time. It's not us. It's physics. And, well, In a strange way, that makes it even more beautiful. Picture, for a moment, a single particle drifting through space. It collides with another, and their states become entangled. That entanglement spreads into the environment, and in the language of quantum mechanics, the world branches. A new reality forms in which the particle scattered slightly to the left. Another forms where it scattered slightly to the right. And, because every interaction is a kind of measurement, a kind of tiny dialogue between particles, the branching never stops. It expands outward like ripples in a pond, weaving a tapestry of universes that grow and grow with every passing moment. The remarkable thing is that this branching isn't dramatic. It isn't explosive. It isn't cinematic. It is quiet. It is subtle. It is the ordinary consequence of the equations, unfolding with the stillness of a dawn tide. We tend to imagine parallel universes as enormous things, cosmic, mind-bending, majestic. But in quantum mechanics, they begin in the tiniest places, in the tremble of an electron, in the faintest shift of a photon's path. Well, think back to something as simple as decoherence. Decoherence is what happens when a quantum system becomes overwhelmed by interactions with its environment. Each of those interactions is a fork, a split, a divergence. And because matter is constantly interacting, vibrating, scattering, exchanging energy, the forks multiply beyond comprehension. 1 second of reality contains more branches than there are atoms in the observable universe. So, it becomes clear that we are not living in a static world. We are living in what I sometimes imagine as a shimmering quantum waterfall, cascading into countless rivulets. A universe that is not fixed but fluid, not singular but endlessly unfolding. And, perhaps the most humbling part is that each of these branches is as real as the one we experience. Not imagined, not hypothetical, but genuine threads in the quantum tapestry. The universe doesn't choose one outcome. It keeps them all. It's not just this world, but also the world that could have been, and the world after that, and the world beyond that, each following the laws of physics as faithfully as ours does. When you pick up a cup of tea, your brain fires neurons. Your hand moves. The ceramic warms your fingers. But beneath that apparent singular action lies a vast branching structure. Photons bounce off the cup and into your eyes. Branch. Molecules in your skin vibrate. Branch. Atoms in the cup exchange energy. Branch. And your perception, your conscious experience, becomes entangled with one branch among many, carried forward in that gentle stream of correlations. It's not that you split, exactly. It's that the universe creates versions of you consistent with each outcome. It's not out there. It's in here, inside the quantum processes that make thought possible. And, this is where the many worlds interpretation becomes more than an abstract idea. It becomes a way of understanding why you perceive a single, stable world, while the underlying reality is immeasurably rich and branching beneath your feet. The astonishing part is that this branching happens everywhere, all the time, regardless of whether anyone is watching. The universe does not require a human observer to make choices. It doesn't wait for us. It simply evolves. Every atom in every star, every grain of dust floating through interstellar clouds, every molecule drifting through Earth's oceans participates in this constant branching. The cosmos is a living quilt, continuously embroidered by quantum events. And, well, when we take this seriously, when we see branching not as a metaphor, but as a literal description of how the universal wave function evolves, something profound settles into place. We realize that time itself becomes a river delta, not a single stream, but countless channels spreading outward. And each channel feels like the only one because decoherence isolates it so completely from the others. We grow older, clocks tick, but beneath that steady ticking lies a froth of quantum possibility, billions upon billions of interactions generating new timelines, new worlds, new versions of events. The arrow of time emerges not from collapse, but from the spreading web of entanglement, the loss of coherence between branches. Entropy increases, correlations scatter. The world becomes classical because the universe keeps branching. Imagine watching a film of reality at the smallest scales. Every frame would reveal micro-branches, tiny differences in particle trajectories. But zoom out, and the branching becomes the familiar flow of time that carries us from moment to moment. The past becomes the set of branches that all converge into our present. The future is the vast fan of branches spreading outward from this instant. And here, in this vision, we see why Everett's idea is so powerful. It removes the need for mysterious collapses. It removes the need for hidden variables. It allows the equations of quantum mechanics to evolve smoothly and deterministically. The branching is not an extra rule. It is a consequence of the rule. The world doesn't collapse. It decoheres. So, perhaps the most remarkable thing is that our sense of continuity, of living in a single, unbroken timeline, is simply the result of decoherent stitching each moment to the next within one branch. Each version of you inherits the memory of the version before, even as countless other versions diverge quietly, invisibly, forever beyond reach. And, though this might feel overwhelming, even existentially dizzying, I often find in it a kind of deep calm, a reminder that the universe is vast in ways we cannot fully grasp, a reminder that our experience, though only one branch, is precious precisely because it is ours. We may not inhabit all branches, but we inhabit this one, and this version of ourselves, this thread of memory and perception, is as real and meaningful as any other. Still, well, this raises another question, one that has lingered on the horizon of physics for decades. If the universe branches so relentlessly, could there be evidence of other branches? Could the cosmos itself carry scars or signatures of these deeper structures? Could the early universe, the universe before atoms, before stars, before galaxies, hold the key? That question pulls us outward now, beyond the quantum world, and into the cosmic one. Because if every moment branches at the smallest scales, then perhaps the earliest moment of all, the birth of the universe, also branched. Perhaps the afterglow of creation itself still carries faint whispers of these possibilities. The universe does not just weave at the quantum level. It may weave at the cosmological level too. And, that path, that bridge from quantum branching to cosmic fingerprints, leads us directly toward a different kind of relic. A relic of light older than any star, older than any atom. The faint afterglow of the Big Bang itself, the cosmic microwave background. And so, it is toward that ancient light, that silent map of the universe's first moments, that we now gently turn, letting the branching of reality guide us into the vast, cold dawn of cosmology. And, as we turn toward that ancient light, the remnant glow of the universe's first breath, we find ourselves stepping into a space that feels, in a quiet way, almost sacred. Because the cosmic microwave background is not just radiation. It's not just a measurement on a satellite map. It is, well, the oldest photograph we possess of reality itself. A picture taken long before galaxies formed, long before atoms cooled, long before the cosmos became the intricate place it is now. The remarkable thing's that this light has traveled across almost the entire age of the universe to reach us, stretched into microwaves by the expansion of space, softened like a memory that refuses to fade completely. And yet it carries with it extraordinary detail, tiny temperature variations, minute fluctuations in density, echoes of quantum ripples that were blown up to cosmic scale during the earliest moments of inflation. Imagine standing at the edge of creation with a camera and snapping a photo just as the universe becomes transparent for the first time. That is what the CMB represents. The moment the fog lifted. Before that, photons couldn't travel more than a tiny fraction of a centimeter before scattering. After that, they were free, and they have been traveling ever since. So, when we examine the CMB today, we're not just analyzing ancient light. We're reading a page from the universe's diary, a page written in temperature and density, in warm and cool patches scattered across the sky like freckles left over from the dawn of time. And, it is within this delicate speckling that something strange appears. Something that doesn't quite fit the simplicity of the standard Big Bang model. A region of the sky colder than it should be, larger than statistical variation suggests. The famous cold spot. Now, well, the cold spot is not a mystery in the sense of a ghost story. It's not spooky. It's simply unexpected. The universe, according to our best models, should have random temperature fluctuations of certain sizes, and most of the CMB map fits those expectations beautifully. But the cold spot is bigger, deeper, and more coherent than we would predict by chance alone. And, that lingering oddity invites questions. It has for years. It sits there on the map like a fingerprint smudged on an ancient photograph. You can ignore it if you wish, or you can lean in and wonder whether something extraordinary touched the universe in those early moments. Some explanations are conservative. Perhaps it's just a statistical fluke. Perhaps the maps look surprising because randomness itself can occasionally produce patterns. But, the deeper analyses suggest that the likelihood of such a feature arising purely by chance is surprisingly low. Not impossible. Nature does allow for improbable outcomes, but low enough that physicists began to ask whether something else might be at work. Well, another idea is that the cold spot could be caused by a massive void, an enormous region of space with fewer galaxies than expected. Light passing through such a void would lose energy in subtle ways, producing a slightly colder region in the CMB. But the surveys we've conducted haven't revealed a void large enough or deep enough to fully account for the anomaly. So, we come to the more adventurous possibilities. One of them, though still highly speculative, is that the cold spot could be the lingering trace of a collision. Not between stars or galaxies, but between universes. And, before that sounds too fantastical, consider this. Inflationary cosmology, the idea that the universe underwent an unimaginably rapid expansion in its first fraction of a second, naturally predicts that many universes might form. Not just one, but countless cosmic bubbles, each expanding in its own region of the inflating field, each with its own physical constants, its own structure, its own timeline. Our universe, in this picture, is just one bubble in a vast, perhaps infinite, foam of universes. Now, if two such bubbles were to form close enough during inflation, they could collide. And such a collision, according to the mathematics, could leave a circular imprint on the CMB, a region slightly hotter or colder, depending on the details of the impact. The cold spot matches some of these predictions. Not perfectly, not conclusively, but well enough that cosmologists take the idea seriously, even if cautiously. It is not just science fiction, it is a hypothesis tested through equations, models, and observational data. And that's the thing. The universe occasionally whispers hints at a deeper structure, and the cold spot feels like one such whisper. Not a shout, not a proclamation, but a quiet suggestion that our reality might be part of something larger. But we must be humble. The cold spot is not proof. It is a clue. And clues are invitations. They ask us to look closer, to refine our models, to seek new observations. They remind us that science lives in the balance between what we know and what we suspect. When we look at the CMB map, this modeled image of warm and cool patches spread across the entire sky, it is easy to forget what we're seeing. These temperature differences arise from quantum fluctuations magnified to cosmic scale. It's not that the early universe was chaotic. It's that the seeds of structure, the seeds of galaxies, the seeds of everything we have become were laid out in these tiny ripples. The cold spot, in that sense, might be a ripple with a story that doesn't quite match the others, a story that could hint at a deeper reality, a hidden interaction, a cosmic neighbor brushing gently against our universe in its infancy. And, well, if that idea is true, even in the faintest way, then the CMB becomes not just a window into the past, but a window between worlds. The light we observe is ancient, but the possibilities it contains are timeless. So, as we contemplate the cold spot, we're not simply asking whether our universe once collided with another. We're asking what it means to live in a cosmos where such collisions could happen at all. We're asking whether the grand structure of space might be bigger, richer, more diverse than the single universe we experience. We're asking whether the multiverse, a concept once dismissed as speculative, might be written in the sky itself. And, there is something profoundly moving about that. Something that makes the night sky feel less lonely, less empty. If the cold spot is a hint of another universe, then we are not isolated cosmic wanderers, but part of a vast archipelago of realities. Of course, we proceed with caution, with equations, with data, not with wishes. But the beauty of science is that it lets us hold wonder and skepticism together. Not just imagination, but also evidence. Not just mystery, but also method. When I look at the CMB map, I feel as though I'm reading a cosmic poem written long before life emerged on Earth. A poem of beginnings, of fluctuations, of potential. And within that poem lies a verse that doesn't quite rhyme. The cold spot. Subtle, persistent, enigmatic. Maybe it is nothing. Maybe it is everything. Whether it exists as a signature of another universe, or simply as an improbable event within our own, it invites us to take the next step, to explore models that reach beyond the standard picture. So, let us follow that invitation now, because if the universe truly inflated into countless bubbles, then collisions are not just possible, they are inevitable. And the cold spot may be the first place where we catch a glimpse of that cosmic architecture. And, as the traces of that ancient light lead us deeper into speculation and theory, we turn naturally toward one of the boldest ideas in modern cosmology, the idea that universes, like bubbles in a vast cosmic froth, can expand, drift, and yes, even collide. And, as we follow that whisper of possibility from the cold spot outward into the deeper currents of theory, we inevitably arrive at a place where the imagination stretches almost as far as the mathematics allows. A place where universes are not solitary, but social. A place where space itself bubbles, inflates, divides, and collides. And so, we step now into the idea of bubble universes, into the strange notion that our cosmos is only one pocket in a much larger, ever-expanding sea. Well, it begins with eternal inflation, an extension of the inflationary model that shaped the early universe. In ordinary inflation, space expands incredibly rapidly for a brief moment, smoothing out irregularities, setting the stage for the cosmos we see today. But in eternal inflation, the inflation never fully ends. Some regions stop inflating and become bubble universes like ours. Others continue expanding, birthing more bubbles, each with its own laws of physics, its own constants, its own potential for galaxies, planets, and perhaps even life. The astonishing part is that this idea wasn't dreamed up as science fiction. It falls out of the very mathematics that cosmologists use to describe the early universe. Quantum fields fluctuate. Those fluctuations produce regions where inflation ends and regions where it continues. And from this simple mechanism, an unimaginably vast multiverse emerges, not just a few bubbles, but perhaps an infinite froth of realities. And, if we picture this, we begin to see how two bubbles might meet. Inflation drives them apart, but occasionally, two expanding universes form close enough that their boundaries collide. It's not a crash like meteors or planets. It's more like two soap bubbles touching, gentle in shape, profound in consequence. The collision could leave a subtle imprint on each universe, an after effect frozen into its structure. So, if our universe once brushed against another in its infancy, what would the evidence look like? It wouldn't be a tear in the sky or a rupture in space. It would be something quiet, something round, a circular pattern in the cosmic microwave background, a faint ring where the temperature is slightly different from its surroundings. And, that is precisely why the cold spot continues to provoke curiosity. It is not proof, but it resembles, in some respects, the sort of signature predicted by bubble collision models, a smooth region, cooler than expected, coherent across a wide angle. Not random noise, but the echo of an event older than any star. Now, we must be careful. Cosmology thrives on humility. The cold spot could still be a statistical anomaly. It could still be a void. It could still be something we simply haven't understood. But the possibility of a bubble collision is not frivolous. It is grounded in the same inflationary theory that explains why the universe is flat, why it is homogeneous, why the CMB looks the way it does. And when we allow ourselves to entertain the idea, even briefly, something remarkable happens. We begin to see ourselves differently, not just as residents of a universe, but residents of a bubble, not just within space, but generated by the same physical process that continually spawns new cosmic regions elsewhere. Well, imagine two universes touching. For a fraction of a moment, so brief it defies any meaningful sense of time, the energy fields at their boundaries interact. That interaction ripples into each universe, leaving behind a mark. We cannot travel to that boundary. We cannot witness the event directly. But perhaps we can read its signature in the soft microwaves that fill the sky. That idea carries a humble sort of beauty. It reminds us that the universe does not need to be centered on us to be meaningful. It suggests instead that the cosmos is generous with its structure, that it allows for countless histories and countless possibilities. And, well, the mathematics shows that such collisions are not rare in the grand landscape of eternal inflation. They are expected. They are natural. They may be happening right now, expanding beyond horizons we will never see. In this larger view, the multiverse becomes not merely a theoretical construct, but a kind of cosmic ecology. Bubbles forming, drifting, expanding, meeting, imprinting. But, if collisions are common, why do we see only one cold spot? Why not many scars across the CMB? The answer may be simple. Our universe is vast, but not infinitely old. We see only the observable region, a tiny patch of the entire cosmos. If a collision happened close enough to leave a mark, then perhaps we are lucky to have even one. Still, so, science demands discipline. Even as the idea of a bubble collision ignites the imagination, it must also pass through the filter of observational scrutiny. That is why physicists run simulations, refine models, compare predicted shapes with the real CMB maps. Some models match moderately well, none match perfectly. And the search continues. In the spirit of scientific honesty, it's worth remembering that data is subtle. Noise can masquerade as signal. Patterns can emerge from randomness. But equally, profound truths can hide behind statistical shadows. The task is not to leap to conclusions, but to keep asking, keep testing, keep refining. And that process has already yielded something valuable, even without certainty. It has led us to consider that the universe is not isolated. That reality may extend beyond the cosmic horizon. That our bubble may be one of many born in an inflationary sea. This perspective shifts how we understand everything, from the origin of physical laws to the delicate balance of forces that allow matter to exist. If countless universes form with different parameters, then our universe's properties may not be unique at all. They may be environmental, a result of where and when our bubble formed. Well, this doesn't diminish the wonder of our cosmos. If anything, it deepens it. We see ourselves not as the center of reality, but as part of a greater whole, a grand structure far beyond comprehension. And the cold spot, whether or not it is the signature of a collision, serves as a reminder that mysteries remain, that ancient light still carries secrets waiting to be unveiled. And, as we contemplate these possibilities, we find ourselves drifting into even bolder territory. Because if bubble collisions are real, if universes can touch, then we must ask what lies beyond the bubble framework itself. What shapes these bubbles? What governs their formation? What deeper fabric do they float within? This is where theoretical physics reaches beyond inflation and into new realms, into the idea that our entire universe might be a three-dimensional brain floating in a higher dimensional space. That the collisions we interpret as bubble impacts might instead be collisions of brains, vast membranes drifting in an unseen hyperspace. And so, from the soft imprint of an ancient cold spot, our journey now moves toward the deeper, stranger architecture suggested by string theory and brain cosmology. Toward a universe that might be a membrane among many, part of a higher dimensional dance, toward the structures that inflation alone cannot fully describe. And, as we drift from the idea of bubble universes into something even grander, even more abstract, we begin to sense that the fabric beneath our cosmos might be richer than the fabric within it. It's as though the universe is not merely floating in space, but resting upon something deeper, something with more dimensions than the ones we move through each day. And so, we enter the realm of string theory and brain cosmology, where the universe is not just vast but layered, and where collisions are not between bubbles of inflating fields, but between immense, multidimensional membranes. Well, string theory begins with a simple and audacious idea that the fundamental building blocks of nature are not point particles, but tiny vibrating strings. These strings can be open or closed, looping back upon themselves, and their vibrations determine the particles we observe. Electrons, quarks, photons, all just different notes played by the same cosmic instrument. And this is where the theory becomes astonishingly bold. These strings require more dimensions than the familiar 3 of space and 1 of time. The mathematics of string theory insists on extra dimensions, 6, 7, or more, curled up so tightly we never notice them. It's not that these dimensions are out there, it's in here, interwoven into the deepest architecture of every particle, every interaction. And as strange as it sounds, this idea brings unexpected clarity, offering ways to unify gravity with quantum mechanics, ways to explain the forces of nature within a single framework. But string theory doesn't merely introduce extra dimensions. It introduces brains, higher dimensional surfaces that can extend through this larger space. Our universe, according to brain cosmology, might be one such brain, a vast 3-dimensional membrane floating within a higher dimensional expanse, sometimes called the bulk. Imagine a sheet of paper drifting in a room. The sheet is 2-dimensional, but the room is 3-dimensional. Now imagine countless sheets drifting, folding, colliding. That is the picture brain cosmology paints, but with far more dimensions. Our universe is the sheet. The higher dimensional space is the room, and other sheets, other brains, could drift alongside ours. And, well, when 2 brains collide, the energy released could be immense, enough to trigger a Big Bang. In some models, this is not only possible but cyclical, a recurring dance where universes are created when brains touch, pull apart, and drift, only to collide again in the distant future. Time itself, in these models, becomes a rhythm, not a linear progression. Well, if this sounds like myth, it is myth shaped by mathematics, myth tested against observation. And remarkably, some versions of brain cosmology predict structures in the universe that resemble the signatures of bubble collisions, temperature anomalies, circular imprints, strange features in the CMB like the cold spot. It's not that string theory proves collisions, but also that it provides new ways to imagine them. Not just universes bumping into each other like cosmic balloons, but entire membranes slamming together along vast surfaces, releasing bursts of energy that echo across space-time. And, this idea changes how we see the cold spot again. Perhaps it was a bubble collision. Perhaps it was something else entirely. A ripple from a brain interaction in the higher dimensional bulk. Whether it exists as evidence or as coincidence, it invites us to imagine. And science begins with imagination disciplined by mathematics. The beauty of brain cosmology is that it reframes our place in the universe. We tend to think of the cosmos as everything. But in this picture, the cosmos is just one region of a grander structure. The laws of physics we know may be local to our brain. Other brains may hold other laws, other constants, other forms of matter. The multiverse becomes not just an idea of multiple universes, but an architecture of many brains floating in a high-dimensional ocean. And there's something strangely intimate about this, because if brain collisions shape universes, then our own existence, our galaxies, our atoms were born from an event not within space, but between spaces. We carry within us the imprint of a higher dimensional collision, a cosmic moment where two brains touched and the energy blossomed into stars, planets, and life. That thought reshapes everything, doesn't it? It reminds us that the Big Bang might not have been an isolated miracle, but part of a larger tapestry. Not just an explosion, but a point of contact. Not just a beginning, but a consequence. And string theory hints at even deeper connections. If strings vibrate in multiple dimensions, perhaps gravity itself leaks between brains. Perhaps the weakness of gravity compared to other forces is a sign that gravity is not bound to our brain at all. Perhaps we feel only a faint echo of the gravitational field, while the true force spans the higher dimensional bulk. Well, some physicists even speculate that dark matter or dark energy could be symptoms of neighboring brains pulling on ours, or of energy trapped in the extra dimensions. It's not proven, far from it, but the mathematics permits it. And the mathematics, once again, invites us into wonder. And, as we look toward the cold spot and similar anomalies, brain cosmology becomes a lens through which we can reinterpret them. A collision of brains might leave ring-like features. It might perturb the density of matter in subtle ways. It might create structures we have not yet recognized. But we must be cautious. These theories are bold. They are elegant. They are tempting. And, well, they remain incomplete. String theory has not yet delivered the testable predictions needed to confirm it. Brain cosmology is beautiful, but beauty is not proof. Still, so, there is value in these ideas. They guide our questions. They shape the experiments we design. They expand the horizon of what we think the universe might be. They spark curiosity, and curiosity is the beginning of knowledge. And, if we imagine these brains drifting silently through the bulk, we can't help but wonder, what traces might such cosmic events leave behind? What signals would travel across space-time, or beyond space-time, as universes touch and recoil? What kinds of waves, distortions, or patterns might we detect? The answer leads us naturally to another frontier, because if universes collide, if brains meet, the event would not only heat the cosmos, but also shake space-time itself. It would send vibrations across the deep structure of reality, not just light, but also gravitational waves. And, that thought guides us now toward the next chapter, the search for ancient tremors, the quest to detect the faint gravitational echoes of cosmic events so old, so vast, so powerful that they might reveal the scars of multiversal interactions. And, as we drift from the idea of brains colliding in higher dimensional space, a new question rises quietly, almost like a vibration felt before it is heard. If universes can collide, if membranes can ripple and shudder in the bulk, then would those tremors not echo across space-time? Would they not send waves through the very geometry of existence? And, that thought guides us inevitably toward gravitational waves, those faint, elusive ripples predicted by Einstein and detected for the first time just a few years ago. Well, these waves are not ordinary waves. They are not waves in air, or water, or light. They are waves of space-time itself, waves that stretch and squeeze reality as they travel. And the beautiful thing is that they carry information not about surfaces or objects, but about the motions of mass and energy in the deepest sense. Imagine tossing a stone into a pond. Ripples spread outward, carrying the story of the stone's fall. Now imagine two black holes spiraling together, colliding in an enormous burst of energy. The ripples those black holes create spread through the universe, not in water, but in space-time, telling us of a dance that took place millions or billions of years ago. That is what gravitational wave observatories like LIGO and Virgo have begun to detect. Tiny flickers, changes in length smaller than a proton, that tell us the universe is alive with motion and history. And, if collisions between stars and black holes create waves, then what about collisions between universes? What about brains? Well, the mathematics suggests that such collisions would indeed produce waves. Waves older than stars, older than galaxies, older than the CMB itself. These would be primordial gravitational waves, born in the earliest moments of the cosmos. And if they exist, their signatures might still linger, faint but detectable, woven into the background of space-time like ancient scars. But detecting them is incredibly difficult. Ordinary gravitational waves from black holes and neutron stars are loud by cosmic standards. They ring like bells. But primordial waves are soft, delicate, stretched by cosmic expansion until their frequencies fall below what ground-based detectors can hear. So, scientists turn their attention to new instruments, space-based detectors like LISA, the Laser Interferometer Space Antenna. LISA will float in the quiet of space, far from seismic noise, with 3 spacecraft forming a giant triangle millions of kilometers wide. This gives it sensitivity to long wavelength waves, waves that ground detectors can never catch. And then there are missions like Euclid and the Roman Space Telescope, which map the structure of the universe with exquisite precision. Though they do not measure gravitational waves directly, they trace how matter clumps and flows, patterns that may reveal the influence of primordial waves rippling through the early cosmos. And, well, CMB Stage 4 projects, the next generation of cosmic microwave observatories, look for tiny polarization patterns in the CMB caused by primordial gravitational waves. These patterns, if found, would be like fingerprints left behind by violent events in the earliest moments of existence. Not just inflation, but also collisions. Not just quantum fluctuations, but also interactions with neighboring universes or brains. The universe keeps these secrets tightly, but it does leave clues, subtle as faint scratches on an ancient relic. Well, gravitational waves are, in a sense, the deepest messengers we have. Light can be blocked, particles can be scattered, but gravitational waves pass through matter almost untouched. They carry pristine information. They carry the shape of events that would otherwise be lost forever. And, if two brains collided, if a bubble universe brushed against ours, gravitational waves could be among the only signals capable of reaching us across such cosmic distances and such vast differences in dimensionality. It's not that they would tell us everything, but also that they might tell us something. A whisper, a tremor, a resonance. We are only beginning to tune our ears to these cosmic symphonies. LIGO and Virgo have detected dozens of events so far, each one expanding our sense of what's possible. And future detectors, like LISA and the Einstein telescope, will reach further back in time, further down the spectrum, further into the origins of reality itself. So, when scientists speak of detecting signatures of multiverse interactions, They are not indulging in fantasy. They are recognizing that gravitational waves offer a unique, perhaps singular window into events that occurred before the universe became transparent to light. Light cannot show us the first moments, but gravity can. Consider this. If brain collisions are real, then some gravitational waves might not originate within our universe at all. They might leak from higher dimensions or be imprinted on the geometry of our brain from beyond. Whether that could ever be isolated as evidence is uncertain, but the possibility alone pushes the boundaries of what we can imagine. And that is the essence of scientific exploration. We listen for signals we do not yet know how to interpret. We look for patterns we cannot yet explain. We build instruments that reach beyond the limits of our current understanding, trusting that nature will surprise us, as it always has. Gravitational wave astronomy is still young. In 2025, it feels like radio astronomy did a century ago, full of promise, full of mystery. One day, we may detect not just black hole mergers, but the faint hum of the Big Bang itself, the relic tremors of inflation, the low-frequency rumble of cosmic strings stretching across space-time. And if those signals carry anomalies, frequencies too smooth, too coherent, too structured to arise from inflation alone, then perhaps they will point toward something more. Something like the aftermath of a cosmic collision. Something like a neighboring universe brushing ours in the earliest epoch. Something like brains meeting in the bulk. Whether this will happen soon, or whether it will happen at all, remains uncertain. But uncertainty is not a barrier. It is an invitation. We grow older, clocks tick, but the universe remains patient. It holds its secrets until we build the tools capable of hearing them. And, the more we listen, the more we discover that reality vibrates at every scale. From the trembling of quantum particles to the echoing waves of colliding stars to the soft, primordial rumble that might lie beneath it all. So, as gravitational wave detectors advance, as new missions rise into orbit, as cosmic maps become sharper, we inch closer to the possibility of detecting not just the events within our universe, but the traces of events that shaped our universe. A collision, a ripple, a beginning. And now, from these faint gravitational echoes, our path leads naturally toward another frontier, one not in the sky, but in the laboratory, toward quantum technologies that may reveal the deeper logic of the multiverse through their impossible power, toward machines that compute not just with zeros and ones, but with superpositions and interference, toward the strange engines that some physicists believe draw upon the structure of many worlds themselves, toward quantum computing, and the unsettling possibility that its extraordinary capabilities hint at the vastness of the reality beneath our feet. And, as we drift from those faint gravitational echoes and the promise that they may hold, our attention shifts from the cosmos back into the laboratory, from galaxies colliding to qubits humming softly in shielded chambers. It is almost poetic, really, that after wandering so far into the vastness of space-time, we now look inward toward machines so delicate that even the warmth of a human breath could collapse their quantum states. And, this shift feels fitting, because the search for the multiverse may not be found only in the stars. It may also be hinted at in the logic gates of quantum computers. Quantum computing rests on principles we've already traced through earlier chapters. The quiet majesty of superposition, the profound intimacy of entanglement, the shimmering uncertainty that defines the quantum world at its core. When we say a qubit can be 0 and 1 at the same time, we're not being metaphorical. We mean it literally. It is not simply here, but also there. Not just this state, but also that one. And the power of quantum computing emerges from allowing these possibilities to coexist, interfere, and guide computation. The remarkable thing is that this superposition isn't merely a theoretical curiosity. It is a resource. A qubit can explore multiple computational pathways simultaneously. 2 qubits can explore even more. And, as the number of qubits grows, the number of possible pathways grows exponentially, far beyond anything a classical computer could ever hope to simulate. This is where David Deutsch, one of the pioneers of quantum computation, offered a bold interpretation. He suggested that the extraordinary power of quantum computers might be evidence that many worlds truly exist. That when a quantum computer calculates, it doesn't just explore multiple possibilities abstractly, but physically across the branching structure of the multiverse. That each branch contributes its own calculation, and the final result arises from the interference of all those parallel computations. It's not the only interpretation. It's not the only story. But it is a compelling one, shaped by the mathematics and by the sheer scale of the computational power that quantum systems appear capable of achieving. And, it forces us to confront a deeper question. Why does a quantum computer outperform a classical one? What physical mechanism allows it to reach past the limits of ordinary computation? Some physicists argue that the explanation lies purely in the elegant geometry of Hilbert space, that the multiverse language is poetic rather than literal. Others argue that the Hilbert space is the multiverse, a mathematical reflection of branching realities. We may not have an answer yet, but the fact that we must even consider such possibilities reveals just how strange the quantum world truly is. Imagine a quantum algorithm exploring an enormous landscape of possibilities. A classical computer would walk along one path at a time. A quantum computer, by contrast, spreads out like a wave, rippling across the landscape, evaluating many routes simultaneously. And through interference, it cancels the paths that lead to wrong answers while enhancing the ones that lead to the correct solution. It almost feels like coordination across realities. Whether that is truly what is happening, or whether it is simply another way of framing an incredibly elegant mathematical process, remains one of the quiet arguments in modern physics. And, it's important to say this clearly. Quantum computing does not prove the existence of the multiverse. Science demands evidence, not merely beauty. But what quantum computing does is force us to take these ideas seriously. It shows us that the quantum world is capable of feats that defy classical intuition, and it suggests, gently, that the architecture of reality might be far richer than we once assumed. The delicacy of these machines is also a reminder of just how fragile quantum phenomena are. Qubits must be shielded from the world because the world, warm, chaotic, full of interacting atoms, would destroy their coherence. Every stray vibration, every photon, every whisper of the environment tries to pull the qubit out of superposition, collapse its possibilities, and pin it into a definite classical state. In that sense, quantum computers are like tiny islands where the branching structure of reality remains exposed, uncluttered by decoherence, preserved long enough for computation to unfold. And perhaps, that's why they fascinate us so deeply. They give us a glimpse, brief, fragile, astonishing, into the domain where the universe still behaves like a wave of possibilities. And, well, the more powerful quantum computers become, the more they reveal. Shor's algorithm, for instance, can factor enormous numbers efficiently, something classical computers struggle with. Grover's algorithm can search unsorted databases more swiftly than any classical method. These aren't just clever tricks. They are demonstrations that quantum mechanics offers computational resources fundamentally different from classical physics. We grow older, clocks tick, but the quantum world beneath our daily experience remains timeless in its principles, coherent, superposed, entangled. And quantum technologies allow us to touch that world, however briefly, however carefully. Well, some physicists speculate that quantum computers might one day detect extremely subtle patterns, microscopic deviations from expected behavior, that could hint at the structure of the multiverse. Not through dramatic events, but through the fine details of interference, coherence, and computational scaling. It's not that we would communicate with other branches, but also that the influence of those branches might shape how quantum information behaves, even if only indirectly, even if only mathematically. And, this moves us into philosophical territory as well. If quantum computation draws upon the structure of the multiverse, then every calculation we perform is, in a way, a collaboration across branches. Not that we feel it, not that we perceive it, but that the mathematics allows it. And that realization, whether literal or interpretative, reshapes how we think about computation, about information, about the universe itself. Still, so, we should remain grounded. As enticing as Deutsch's argument is, experimental evidence does not yet say the multiverse exists. What it does say is this: quantum computers behave as though reality is structured in a profoundly non-classical way. And whether that underlying structure is many worlds or something else entirely, it compels us to keep looking deeper. And perhaps this is the most human part of the story. Quantum computing reminds us of the limits of our perception. Our senses evolved to navigate the classical world, not the quantum one. So when we build machines that reveal quantum behavior, we are building instruments that reveal the limitations of our own minds. It's not that the universe is mysterious. It's that we are only beginning to develop the tools to understand its deeper patterns. And, as these machines grow in capability, as they step from dozens of qubits to hundreds, then thousands, the strange frontier they reveal will grow wider. And maybe, somewhere in that widening frontier, we will find clues, not proofs, but clues, about the branching nature of reality. And now, from these shimmering qubits and the philosophical questions they invite, our path leads naturally to the most human frontier of all, ourselves. Because if reality branches, if countless versions of events unfold beyond our awareness, then what does that mean for choice, for identity, for responsibility, for free will? So, from the hum of quantum processors, our journey now turns toward the quiet, introspective questions at the edge of physics and philosophy. Questions about the limits of human perception and the meaning of choosing in a multiverse. And, as our journey passes from quantum processors into the quiet, human territory they inevitably lead us toward, a softer question begins to form. One that physics cannot avoid, no matter how vast its equations or how elegant its theories. Because if reality branches with every interaction, if countless versions of events unfold beyond the reach of our senses, then what does it mean to choose? What does it mean to be conscious? What does it mean to be you in a universe that forever divides? Well, let's begin slowly. In the many worlds picture, each decision you might make, every hesitation, every tiny thought, does not split reality in some dramatic, cinematic way. It is the underlying quantum interactions in your brain, the neurons firing or not firing, the molecules shifting one way or another, that define the branching. Not just big choices, but also the smallest processes, the ripples that build thought itself. And, that can feel unsettling at first, because we tend to think of ourselves as singular, continuous. We imagine a single timeline stretching behind us and ahead of us, a single identity walking along it. But quantum mechanics whispers that beneath this familiar story lies something else, a proliferation of possibilities, each entangled with a different version of what you might become. It doesn't mean the self is an illusion, but it does mean the self is local. You're the version of yourself in this branch, on this timeline, following this set of correlations inherited from the past. And every choice you make becomes part of this branch's internal logic, its narrative, its coherence. Some people hear this and think it diminishes free will. But perhaps it's not that simple. Perhaps it's not that free will disappears, but also that it changes shape. It's not that choices don't matter, it's that choices matter within the timeline you inhabit. You cannot steer all branches. You cannot influence a version of you you will never meet. But within this branch, this lived reality, you move freely, consciously, meaningfully. And, well, that means responsibility still holds its weight. The fact that other branches exist does not excuse the actions taken here. It doesn't soften the consequences. It doesn't make the emotional texture of your life less significant. If anything, it sharpens it. It says, this version of you, this reality, is uniquely yours. Among the countless branches, this one is the only one you will ever feel from the inside. Well, and when we think about perception, the limitations become even clearer. We cannot see across branches. We cannot communicate with other versions of ourselves. The physics simply does not allow it. Decoherence isolates each branch so effectively that any attempt to interact would require undoing the entire web of environmental entanglement, a practical impossibility. Once the branches diverge, they remain separate, not because of walls, but because the universe preserves consistency. The irony is that this isolation is what gives rise to the classical world we experience. Our senses evolved in a reality where decoherence reigns. We detect definite outcomes because the environment records them instantly, scattering information so widely that quantum interference vanishes. It's not that branching hides itself from us deliberately, but also that our biological machinery was shaped in a world where branching is always complete by the time perception happens. And, perhaps that's why free will feels so real. Within a single branch, the flow of time, the unfolding of events, the choices we make, they all feel coherent, unified. The universe does not show us its underlying multiplicity because the multiplicity has already unfolded beyond our reach. So, physics brings us to an important philosophical point. Even if reality branches, even if many versions of us exist, our experiences are inherently singular. You do not wake up in two branches at once. You do not feel the outcomes you did not live. You are not responsible for the decisions made by versions of you that decohered away into unseen worlds. You are responsible only for the life you inhabit. And this is where the beauty emerges. because rather than diminishing your significance, it enhances it. It says that meaning arises from the specific, not the hypothetical, from the lived, not the abstract. From this sequence of moments, the one carried by your memories, your relationships, your fears, your hopes. And, if we look even deeper, the question of free will becomes less about physics and more about perspective. Quantum mechanics does not remove agency. It simply reframes it. Agency is the experience of navigating a branch of reality from the inside, choosing, acting, becoming, while knowing that the universe itself holds more possibilities than any single consciousness could grasp. We grow older, clocks tick, and within the ticking, we make choices. Those choices shape our lives. They matter. They matter because they shape the narrative of this branch. They matter because they form the story you will remember. They matter because they are recorded in the correlations of this universe and no other. Well, this brings us back to the limits of perception. Human beings are not built to sense quantum branching. We do not see the wave function. We do not experience superposition. Our brains, warm and noisy, collapse quantum states long before they reach awareness. And yet, paradoxically, we are products of those same quantum processes. Consciousness emerges from the classical shadow of quantum activity, a shadow shaped by decoherence, tied to one branch at a time. That is why asking whether we can jump between branches or communicate with parallel selves leads nowhere scientifically. The physics does not support it. Branches are not locations. They are correlations. They are histories that cannot recombine. To move between branches would be to rewrite the entire quantum record of the universe, which nature simply does not allow. And, yet, even within this rigidity, there is a sense of openness, a sense that our understanding is still growing, still incomplete. Quantum mechanics has surprised us before. It may surprise us again. But for now, the best we can say is that the multiverse, if it exists, is something we inhabit unconsciously, quietly, through the structure of the wave function, not through deliberate action. So, what does that leave us with? A kind of quiet humility, a recognition that reality is larger than we can see, but also that our experiences within it are no less true because of that. We live one branch at a time. We love one branch at a time. We regret and hope and dream within one sequence of moments. And that is enough. More than enough. In this sense, the multiverse does not diminish the human experience. It magnifies it. Because in a cosmos where countless possibilities exist, the fact that you are here, now, living this particular path, becomes profoundly meaningful. It becomes a reminder that awareness itself is rare, fragile, fleeting, and precious. And, well, this brings us naturally toward the quiet close of our journey. Because after tracing the path from quantum particles to cosmic brains, from superposition to gravitational waves, from branching universes to branching selves, we are left with a deeper question, not about physics, but about our place within it. A question about wonder, a question about meaning, a question about how we carry ourselves in a universe that is larger, stranger, and more beautiful than we ever imagined. And so, with these reflections lingering softly in mind, we step toward the final thoughts that tie this journey together, toward the closing meditation on what it means to ask questions of a universe that forever invites us to listen. And, as we arrive at the quiet end of this long journey, from trembling quantum particles to the vast sweep of cosmic inflation, From the cold whisper of ancient starlight to the humming logic of quantum machines, we find ourselves standing before a single, gently unfolding truth. A truth that feels both humbling and astonishing. That the universe is far larger, far stranger, far more beautiful than our senses ever allowed us to believe. We have watched electrons drift through two slits at once. We have listened to spacetime ripple as black holes spiraled together. We have traced faint scars in the oldest light of the cosmos, and each of these discoveries, delicate yet profound, suggested that reality might not be singular, that the world we inhabit may simply be one path among countless branching paths. Well, but the deeper we looked, the more we learned something quietly important. Science does not seek fantasy. It follows equations. It follows evidence. And sometimes, only sometimes, those equations point toward possibilities so vast that they reshape how we understand our place in everything. And, even if the multiverse exists, even if other universes brushed against ours in the deep silence before atoms formed, what remains constant is our experience here, in this branch, on this timeline, among the people we know, under the stars we recognize. It's not that our lives mean less because other versions might exist, but also that our lives mean more, precisely because this version is the one we feel from the inside. We grow older, clocks tick, and in that steady ticking, we make choices, we remember, we hope. And maybe that is enough. Maybe that is the quiet miracle of being conscious, that in a universe overflowing with possibility, we are given the gift of inhabiting one unfolding story. The purpose of science, then, is not merely to broaden knowledge, though it does that beautifully. It is to remind us that our place in the cosmos, however small, however temporary, is illuminated by curiosity. It is to show us that even when the universe branches endlessly, our desire to understand is uniquely ours. And, well, perhaps that is why we ask these questions at all. Not to master the universe, but to wonder at it, to let ourselves be surprised, to let the cosmos be larger and more mysterious than we dared to imagine. So, as this exploration gently comes to rest, perhaps the most beautiful thought is also the simplest, that we are part of a reality still revealing itself. And by asking these questions, by following the echoes of creation, by contemplating other worlds, by standing at the edge of what we can know, we become participants in the universe's ongoing story. And in that soft realization, we may finally understand what makes this journey so deeply human. Not the idea that countless versions of us might exist, but the wonder that this version is here, now, asking questions that make the universe worth listening to.